So as far as control algorithm options, as far as implementing a strategy, I guess they could fall into two basic ways we could do this. One is use heuristics, or kind of like rules of thumb. The other is to use optimization theory. And so if you haven't seen this before, don't worry about it. But basically, there's a lot of different optimization approaches. There's linear programming. And so when you're doing linear programming, what you need is you need to get this into kind of like a linear set of equations to solve. Given that the power flow is nonlinear, it takes a little bit of effort to do linear programming. In this case, you have what's called mixed integer linear programming. And what this is take into account is the fact that you're going to have some binary states like capacitor switch states, like 0 to 1. There's nonlinear programming. So this is getting into how you handle nonlinear equations like we would see in power flows. And then you have another sort of approach called dynamic programming, which is used a lot of times for coming up with control strategies. So there's a lot of papers on this topic. I mean, if you look in the literature, there's thousands of papers which talk about how you do different types of optimization. And so if you want to learn more about this, usually the sort of class to take would be an operational research class where you learn about these different types of techniques. So we're just going to focus on a heuristic approach, a rule-based approach. And this is assuming that we have some type of controller at the substation. So this could be a substation remote terminal unit. And the objective is to maximize our loss reduction. This means keeps losses small. And we're going to have constraints. And this is how you usually set up these control problems, is you have a constraint. And our constraint would be, we want to keep the voltage at buses we want to control between a minimum and maximum value. Something else we may have as a constraint is we may want to limit the number of capacitor switchings per day. And the example number could be 4. We don't want to have more than 4 operations per day. Then also too, we might have a constraint on our power factor. We need to keep the power factor greater than or equal to some target. And so this could maybe be 0.99. We want to keep it between 0.99 leading and lagging. Another assumption in this case is we have the ability of taking measurements. We not only have top of feeder information, we have bottom of feeder information as well. And this is showing some commercial device terminology here, where PCD is a controller you would maybe have like out in the field near the capacitor, and SCD would be a substation switch controller. And so anyway, these are just IEDs that can take the appropriate measurements and do capacitor switchings if necessary. So in most heuristic assumptions, and this is based, what I'm going to show here is based on a paper that Dr. Brown wrote a number of years ago with a postdoc. But what a lot of approaches are based on, if they're heuristic, is we could decouple the volt and the VAR control problem. So what this means is that if capacitors impact primarily VAR flow, that we figure out what the capacitor setting needs to be. If regulators control voltage, we figure out what the voltage regulator settings need to be. And if needed, we coordinate the two where it becomes necessary. So voltage control is going to be achieved primarily by adjusting the taps on the regulators. We're going to have like a target voltage we're going to try to meet, and we're going to try to keep this voltage within bounds. The other thing we're going to be doing in here is assuming that the caps are primarily going to be switched to minimize losses. They do have effect on the voltage, but in order to come up with this simple control strategy, we're going to be looking at the line regulators for the voltage control and the capacitor banks for the loss minimization. So anyway, this shows the fact that we basically have a kind of like a dual subproblems we're trying to solve here, where we'll kind of focus on the use of the capacitors for minimizing losses and the regulators for the voltage. And if necessary, then what we're going to do is we're going to couple these two together if needed. So just a few notes about the voltage regulator control in this particular paper. Note what they're doing is they're computing a voltage drop between the substation bus and the bottom of the feeder. This is kind of similar to what you would do with line drop compensation that we talked about earlier this semester. So the set point for the regulator is designed to take the drop across the feeder into account. If we take this drop into account, we have to have the top of feeder voltage boosted up a little bit for that. Some other functionality that's in this particular report, and this is kind of similar to what we have for regulators, is that we're going to have a bandwidth setting. We're not going to try to adjust the voltage. If the voltage is within a certain bandwidth, we won't touch it. And what they do in this particular paper is they do a comparison where they look at voltage drops. And if the voltage drops get kind of high, they have one bandwidth. If the voltage drops are low, they use another bandwidth. So the idea in this case is that if you get a lot of voltage drop, you might need to tighten the bandwidth in this case. And then what they're going to be doing in this case is, again, trying to keep the voltage at the load, at a certain point. And if we run into a situation where the voltage gets too high, then we basically put a limitation on the tap change. Conversely, if we get to a point where the voltage is kind of getting high and turning the capacitor bank on may kind of mess us up a little bit, then we can signal the capacitor controller that say, hey, you got to kind of hold off on turning on and off because we're getting pushed up against an upper limit on voltage. And if you switch on to try to minimize loss, you might actually cause the voltage to go above our limit. And so there's different things you have in here because this is not like an optimal control. It's kind of heuristic in nature. And so you have to have these different rules in here for this to work. For the capacitor controller, say this is the primary means for the loss reduction. And what we'll assume if we have multiple capacitors is the largest capacitor gets switched in first. It would get switched out last. If the capacitors are all of equal sizes, then what you do is you would switch the furthest capacitor away first, because basically the thought is that would have the most impact on voltage. So anyway, there's some other sort of things in here on the assumptions, but we'll go ahead and skip that for now. And so for the control procedure, we're looking at the power factor at the top of the circuit. If we have the option, given the size of our capacitors, of making an improvement, if it turns out that the substation reactive power gets above a certain ratio of the downstream capacitor that's next to switch in, then we'll go ahead and switch it on. And then if the Q sub drops to the point where we can actually help squash the reactive power down further, then we'll go ahead and switch that capacitor off. And so we're using kind of multiple, we're using these coefficients on the capacitor side so we don't get cycling on the capacitor banks on and off. This just kind of shows an example of what a SCADA screen could look like for something like this. And this is something we used in the 586 class last fall. We actually had the class members actually put together their own controller based on this. And this is showing the fact you can manually control the tap position or you can manually control the capacitor position, but that what they were doing for this particular project is implementing an algorithm similar to this, where this switching sequence would actually be computed on a central controller. And then we were actually simulating, what would be the effect of of implementing this in the field as far as what you see for changes in measurements and things like that. So this is a one-line diagram associated with this control. So kind of getting into the logic on a more advanced optimization based controller is kind of beyond what we can cover in this class. Again, Usually that's kind of getting the domain of what a lot of the PhD students would be working on. And again, if you say if you're going to take classes in optimization theory, especially in operations research, then you would have a better background for solving this sort of problem. That's how a lot of the commercial algorithms would work. So as far as comparison of what you can do with what control strategy, if you're just using local control, the pro of this is we wouldn't really require any communications to the devices in the field. You don't have any central logic. This is pretty cheap. And so if your loads are pretty predictable and you can engineer this using like a power flow program, this may be the way to go, because you have to base everything on offline studies, which may not match the field conditions. And so to the extent you can predict what's going on with the power flow, you can probably get this to work. But if you're getting different things to happen than what you can work out in your power flow, then this is probably not the best way of approaching this. If you just did VAR dispatch on your capacitors or simple power factor control, you would only need to have a one-way communications, and this is a very simple control, but we're not coordinating with the voltage controls. And then finally, when we get to the integrated Volt-VAR control, this is probably going to give you the best performance. This is actually going to give you the ability of optimizing your circuits. But then we have to spend more money on communications. We need two-way communications. We need to have more complex logic. We have to also have models which are somewhat accurate. So if I don't have an accurate model what's in the field, then I can't really do any optimization around it. But anyway, this is what most utilities are moving to right now, is this integrated Volt-VAR control. Conservation voltage reduction is sort of a subset of integrated Volt-VAR control. And what we're trying to do in this case is intentionally drop the voltage to reduce peak demand. And a typical rule of thumb would be that if I want to get a, say like a 0.7% reduction in demand, I'm going to need about a 1% voltage change. This ratio is what's sometimes referred to as a CVR factor. And so if you talk about a CVR factor of 0.7%, usually the way we index this is that we look at a percent drop in voltage, and we're looking at what we can get for a change in real and reactive power from 1% drop in voltage. And so in this case, the CVR factor would be 0.7%. What I have to watch out for if I want to reduce this voltage, say I'm going to try to reduce the voltage by 3% to get a 2.1% drop in demand, I have to make sure my voltages that are low don't drop below the ANSI restrictions. So usually what we would have seen in the past for average voltage would be something like 122.5. It'd be very typical at customers. If you measure the wall socket voltage, they'd have 122.5 volts. What this means is, without making a lot of circuit improvements, we should have some headroom for doing this sort of control. Maybe not for all the loads in our circuit, but for a lot of the loads in our circuit. So as far as the benefits, I can reduce the need for expensive peak generation. That's primarily why you use CVR. It also has some benefits in reducing consumer energy consumption. And so some public utility commissions may like this because it would reduce the customer bill, could result in some capital expenditure deferrals. And then anything you do as far as reducing peak losses and energy consumption also would have an impact on greenhouse gas. And so some of the business cases look at reduction in greenhouse gas as a side effect or a side benefit of doing this CVR. So the modeling is going to be different in a couple different ways. First thing is we move away from a constant load model, constant power load model. We assume that there's going to be a constant impedance, constant current characteristic. So if I can drop the voltage, I drop P and I drop Q. The other thing I may do in looking at the benefits is I may actually explicitly model the transformer. And the reason I'm doing this is if I can reduce the load, that reduces the I²R loss in the transformer windings. And if I could reduce the voltage, this also is going to reduce the hysteresis and eddy current loss. And so I'll also get some reduction in I squared R on the line as well. And so there's a number of places where we can reduce losses, we reduce energy consumption. And we would need to take this into account if we were looking at a comprehensive business case in this situation. So not only would you have utility side benefits, but you could also claim having some customer side benefits as well. So what we're doing, again, is if I took a regular feeder, probably the voltages would be in this range shown in blue, maybe on the average. This is showing the average around 120 or higher than 120. But basically what CVR involves is not only reducing the voltage down, but then what we also do is we kind of squash the range of voltage down a little bit by preconditioning the circuit or by using better controllers on the circuit. And so we still have to keep the voltage within plus or minus 5% of the customers, but we're going to be very careful that we don't go below this lower limit. So where does this 0.7% come from? Well, this comes from running a lot of studies from utilities trying to do CVR, dropping the voltage, and see what sort of reduction they get. And so this is showing the effect of like a 1% or a 2% or a 3% or a 4% reduction. And there's different sort of tests that have gone in the past. If I'm staying on this straight line, this means I'm getting a 1% CVR factor. But you'll see in a lot of cases that our change in energy, in this case, which is also going to be proportional to change in power, is not on this straight line. It's not on the 1% line. It's actually below this, closer to 0.7%. And what you'll see is different circuits have different levels of benefits. Some circuits we do better than 1%. But other circuits, you know, we could do a lot worse, maybe 0.5%, let's say. It depends on the types of loads we have in the circuits as far as the benefit we get. And so anyway, just realize that for all our feeders, we don't get the same CVR factor. We get different CVR factors depending on the type of loads, and this could actually change as a function of time of year, because a lot of this is based on what type of heating, ventilation, and air conditioning type systems that your customers have on your circuits. So just to see how these benefits could break down, this is a little model I built a long time ago for a consulting project. And what I'm modeling is not only the main feeder, but I'm modeling laterals, I'm modeling transformers, and I'm also modeling customer loads. And so what I'm looking at is I'm looking at being able to control the voltage by adjusting these two voltage points, as well as putting switch capacitors out on the circuit. So if I have a feeder, it's a 5 MVA, 0.85 power factor. This is 12.47 kV feeder. What I can do is I can make assignments for the different feeder impedances and lateral impedances, and I'm assuming in this case a CVR factor of 0.8%. And what you could do is you can kind of play around with different sort of voltage controls and then seeing where you get the benefits at. And so when I start this out, I've got a base case here where I don't do anything with capacitors or line regulators. And what I see is I get a loss percentage of 5.4%. And I can break this down in terms of where the losses are actually at. So this particular circuit's going to have a minimum voltage at 97.65% of nominal. The top of feeder power consumption is 4.293 megawatts. I've got 113 kW loss in the main feeder, 37 kilowatts on the lateral. Transformers have 79 kilowatts of loss as well, where the losses total up to 230. So not a very well-performing circuit in this case. Now what I could do is note when I'm starting with the top of the feeder is 1.05, what I could do is I could put some capacitor banks out there. I've got those at 3 locations right now. And then what I'm doing is I'm dropping the voltage at the substation in this case. All right, so I can put voltage changes at other points in the circuit, but for now I'm just dropping the top of feeder voltage, and I'm putting more capacitance along the feeder. And what you get is, starting what we have in purple, which is kind of a drop as you go down the length of the feeder, you can see if I drop the substation voltage and I put those capacitors in, what I'm doing is I'm leveling out this voltage. And so I'm actually dropping the voltage toward the top of the feeder, and I'm actually boosting it up a little bit toward the end a little bit. Now look at the difference in all these different sort of losses. If I look at my total losses, I go from total losses of 230 down to about 200. The other thing that's going to happen in this case is as far as my customer load, is I also get a drop in the amount of power that's used by my customers. And so what I'm going to see in this case is my customer load drops from 4,037 to about 4,000 kilowatts. And so not only does your load drop off because the loads themselves use less energy, but then you're going to get a drop off in real power consumption and also energy associated with that, because you see less losses in the line, you see less losses in the transformer, and less losses in the lateral. And so anyway, the losses drop off, and you can see these different types of benefits due to having CVR in the circuit. And note the losses don't change a lot, but it just kind of adds up. When you actually need it, you can get the 1 to 2% change in power consumption. That would actually make a big difference as far as meeting your peak load. Another thing that's associated with doing CVR schemes is you need to have a good set of measurements to make sure the voltage doesn't get too low on your circuit. And we could certainly put out standalone measurements for this, but given so many utilities are actually installing smart meters now, it makes a lot of sense to look at the use of meters as an input into an integrated Volt-VAR scheme like CVR. And these types of meters are what's sometimes referred to as bellwether meters, because what we're going to do is just take 1% of the meters that we have in the field and use that 1% of the meter information as feedback into our CVR control. And so if I have a meter out in the field, basically these devices have radios. I can do two-way communications. I can get this information up into an advanced metering infrastructure head-end system, and then get this to my meter data archiving and my distribution management system, which will then use this information right here to make decisions about whether to try to raise the voltage like any further, or maybe we have to boost it up again to make sure we don't inconvenience some of our customers. So anyway, this kind of gets into a little bit what we can do with these meters. And I know we didn't talk about meters in this particular semester, but just realize that utilities are looking at using meter data as feedback mechanisms. And these meters are just kind of low-cost IEDs. You can actually get this voltage information off these devices. The problem is the communication systems typically doesn't have the bandwidth to get this up at a very high speed. But certainly it's a very useful type of information that we could use. One thing I want to get into mention before we get into some of the examples in windmill and OpenDSS is what's kind of the assumption on a CVR effect. So we talked about a machine model having a combination resistance and inductance. And if this voltage goes down, then this power consumption goes down. So the assumption we're making, these loads have a constant impedance sort of characteristics, which motors certainly have and strip heaters would have. But what if we had a power electronic kind of a load? Let's say if we looked at a TV set, an LCD TV set. Well, what you're going to see now that we're moving to power electronic based devices where everything kind of used to be sensitive to voltage, like the old tube TVs or the TV sets of the older types of power supplies, what you would see is if you adjust the voltage on a newer type of TV set, it doesn't change the power consumption any because the power electronics is compensating for the change in voltage. So the power electronics devices, a lot of these devices consume the same amount of real power regardless of the voltage. So as customers would get their heating, ventilating, air conditioning equipment converted over to power electronic based devices, this CVR effect may have a tendency to go away. We're seeing it now with lights. It used to be we had these incandescent light bulbs and you can actually see them dim a little bit, the voltage drops. Now with these newer types of lighting controls, they're power electronic based. And so they're going to have the tendency to consume the same amount of power, regardless of whether you're going to have like a couple % deviation in voltage or not. So there's a lot of questions now about to what degree the CVR effect's going to last. It takes a long time to replace all the air conditioning heating devices out there, but over a long enough period of time, this type of control may not be useful anymore. So anyway, let's let's kind of link this back to the project part 2. There's a lot of barriers also to implementing a CVR strategy. It tends to be kind of a complex business case to make because there's so many different benefits and costs to this. As we saw in our project, if we want to levelize the voltage, this could take a lot of circuit investment. This would be kind of expensive to set up in the first place. And so this is one barrier, is the capital expenditures you'd have to make. The other thing too would be if utility is reducing the voltage and it's reducing the amount of energy consumed by customers, well, the utility is conceivably going to see a loss of revenue from this. And so they'd have to be able to figure out how to compensate for this. Again, this is very dependent on the load makeup. Certain feeders, you may not see a CVR benefit. The other thing too is a lot of the design standards that are in place, focus on reliability and power quality. And if you start reducing voltage, that could actually degrade power quality. And so there's always pushback, by the industry users, by utility folks concerned about utility power quality. Industry power quality. Then if we drop this voltage, we may start to get low voltage points in the circuit that might actually inconvenience customers. So a lot of things you have to look at before deciding to move ahead with the CVR scheme. And so as I mentioned before, feeders typically have voltage profiles where the voltage drops down. It drops down to a pretty low value until we finally boost it back up. And what we have to do CVR is we have to find a way of making sure this voltage is levelized. And so we'll have the headroom needed basically to get the voltages reduced. And then see, we looked at this before, we looked at load balancing, we looked at capacitor placement and line regulators and line upgrades and things like that. And as you can probably guess, the longer the circuit is, the more difficult it is going to be able to do this CVR. So if you have a really, really long circuit, really long circuits tend to have a need for a lot of voltage regulators because they get a lot of drop. So if these circuits are long, they're not very good candidates. Also, especially since these circuits may not have a lot of load, the best candidates for CVR would be relatively short circuits, maybe on the order of 1 or 2 miles, where you don't have a lot of voltage drop to begin with. And so if you don't have a lot of voltage drop going from the top of the feeder down to the bottom, it makes it much, much easier to drop the voltage down at the substation, right? And so a lot of these long feeders with rural customers may not be good candidates for CVR. And probably if utility were going to really do an economic evaluation, they wouldn't put CVR in all their circuits. They would just do a subset of the circuits where it makes more sense to do that. Okay, so one more thing I wanted to mention or get to the examples, is what are these voltages really going to look like at the top of the feeder? And this is actually a set of measurements for utility that's doing demand reduction using CVR. And so you see before the event, before the CVR event, basically this is what you're going to get for the voltages at the top of the feeder. And this is obviously a 12.47 kV circuit where these are line to neutral values. Note that if this is phase A and this is phase B and this is phase C, these voltages are not balanced. The reason being is you have a sub-transmission circuit that's feeding the substation. You've got a three-phase transformer dropping these voltages down, but then what you're going to have coming out is going to be a three-phase line regulator where you have to have the same tap position for each phase. It's not like it's how we're modeling this in our program. This isn't how it is in the field. So what we're going to see when we get below the regulation at the substation is we're going to see imbalanced voltages. This happens because the subtransmission systems, a lot of these, they're not properly transposed. And so you're going to get imbalanced voltage drop across subtransmission, which is going to give you imbalanced voltage at the load side of the regulator at the top of your circuits. And so just kind of keep in mind, this is what this is really going to look like. And what we were doing in class is we were assuming that you had regulation on each phase. And I can make that voltage 124 in phases A, B, and C. Just realize in real life it doesn't work this way. That because of imbalance in the circuit, we're going to have imbalanced voltages at the top of the feeder. What's interesting about this is that when the event occurs, that this voltage drops a little bit more than 3%. Maybe it's doing more like 3.5%, but this is actually showing the initiation of the event. And basically what we're going to do is we're going to take all our voltage regulators and we're just going to drop those all down by about 3%. And so this is actually showing the change that would happen at the top of the circuit. This is actually a real set of field measurements. And so anyway, let's stop this video here and we'll finish things up with a couple examples in Windmill and also in MillSoft.